All right, today we're going to be talking about Chapter 18, which is looking at winds of the world, global and local wind systems. So this is a common weather station recording, uh, which shows all of the different pieces of information that we've looked at so far in weather. It's going to look at things like things we talked about last chapter as dew point and the actual temperature. Uh, and we're going to focus on the right side of this weather station, which is looking at the wind speed, the pressure and pressure trends, if the pressure is increasing or lowering, as well as in this image here, this is showing the sky cover. In this case, it's fully covered with clouds. And in this case, we're getting a little bit of rain. And so when we start looking at this uh, surface model, again, all this information can be put on one small spot on the map. So this way we can plot lots of information on a map. This is a way to see trends starting to develop on a weather map. And one thing that we noted is that weather is not uniform throughout the areas. Um, Wind will develop as air is moving from high pressure to low pressure. And so we call the horizontal movement of air wind. Air moving up is called updrafts, air moving down is called downdrafts. And so when you start looking at this image here, we can clearly see we have an area of high pressure and an area of low pressure. And so the air is moving from the high to the low. Very similar to this, if I had a balloon, I'm going to fill that balloon with air. If I don't tie that balloon off, the air inside the balloon is going to be at a higher pressure than the air outside of the balloon. And so as a result, the air is going to be going from the high pressure to the low pressure, and the air is going to go out of that balloon. And so we can actually measure how much of a difference there is between the high pressure and the low pressure. And when we start looking at the distance that air is traveled, we can look at the pressure gradient. Just like if we were looking at the gradient, or another name for gradient is slope, and this would be the rise over the run. The rise would be the change in air pressure. The run would be the distance in between. And so if we looked at the air pressure, if we had a very short short area with a lot of change, you'd end up with very strong winds. Um, Two other factors which are going to influence the speed and the direction of the winds is going to be the frictional force. And this is simply the impedances on the ground that can slow the wind down. You may see farmers put a row of trees to act as a windbreak, to act as a frictional force that would slow down the wind, and so the wind isn't going to be whipping down, causing soil erosion. And then finally, the Coriolis effect. This effect is going to influence the direction in which the winds are moving. And so what we have here is a satellite image of the atmospheric water vapor in the air, showing that the air has these little currents and eddies. And we're going to look at these different variances in the winds in this chapter. And so again, on the right side of this image, we see a lower pressure, meaning that there's less overlying air. And so in the area on the left part of the image, the air is much more compact. And so that air is going to be going from a high pressure to a low pressure. And this is what was putting wind in their sails in this image here, air going from the high pressure to the low pressure. And the reason why we have difference in pressures is because when air heats up, it's going to expand and be at a lower pressure, especially if the air is starting to rise up. It's going to have less overlying weight pushing down on that air. And then if we have air sinking, that's going to cause the air to get more compact. And if the air is more compact, it's going to be a higher pressure. So this, what causes air to accelerate? Which of the following forces cause air to accelerate to begin to move from one place to the other? And that's the pressure gradient force. The friction would slow it down. And so when we start looking at the pressure gradient here, we can see in this upper image, we have a high pressure at the top of this, a low pressure at this lower portion, and we can see that the pressure lines, or the isobars, lines of equal pressure, are very close together compared to the lower image where they're much further apart. When the air is moving close, or when the isobars are closer, we have a steeper gradient. Again, I can't see the numbers on this image, but if we're having a uniform air pressure isobars, if these are, say, 4 isobars of pressure difference, very closely spaced, very fast moving. We can think of, if we thought of these as contour lines, a very steep gradient, a steep change in elevation of closely spaced isobars. It's going to be closely spaced contour lines is going to be rapids and water moving very fast, steep gradient. And we have the same thing when we look at air pressure. Now, friction occurs when molecules of faster moving molecules collide with slower moving molecules, or when a volume of air shears up against the Earth's surface. And so this is going to slow the air down. And so we can look at this boundary layer here, which is going to effectively cause the air to stop moving if it's causing this impedance. So this boundary layer is you'll notice it mimics the landscape as well. There's a couple of different portions of this boundary here that we're looking at, where these air is adjacent to the air surface, where the friction is significantly affecting this layer. So the third force that we're going to be looking at is that Coriolis force. Now, we've looked at it in the last in the meteorology chapters, and we said that the Earth is spinning. And when we have a spinning Earth in this same direction, if the air was moving from the North Pole to the South Pole, the speeding up of the air as it's going from North Pole to the South Pole is going to deflect it. From the North Pole to the equator is going to deflect the wind to the right. If the air is moving around the equator, it's moving a lot faster. And so as it moves towards the North Pole, it's going to also deflect to the right because that air is moving faster at the equator. And the reason why it's moving faster at the equator, because every day the Earth has to do one lap. And so it's much larger distance around the equator than it is at the North Pole. And so this Coriolis effect is also going to have its effect on the winds. It's not going to affect the speed, it's going to affect only the direction. And so when we start looking at this in the Northern Hemisphere, which force causes the Northern Hemisphere air to veer to the right? We just got done talking about that. That's the Coriolis force. Now, when we start looking at the forces at upper air, we don't really have to worry about the frictional forces because, again, those are occurring at the Earth's surface, Earth-air interface. And so the only thing that we have to worry about in the upper air movements, or the geostrophic air, is the pressure gradient force and the Coriolis force. Now, the Coriolis force affects the direction. And so when we start looking at the total vectors of movement here, the air at point A here is the air is moving from the high pressure to the low pressure. But as that air starts to move, it's getting deflected due to the Coriolis effect. And it's deflecting to the right in the Northern Hemisphere. If we were in the Southern Hemisphere, everything would be deflected to the left. And so when we start looking at this wind, as it's moving, it's deflected more and more to the right as that Coriolis effect is greater and greater. And eventually what's going to happen is the winds are moving parallel to the isobars. And so what's going to happen is when we start looking at these geostrophic winds, or upper air wind flow, about 6 miles above sea level, the air is constantly moving parallel to the isobars. And so when the isobars are closer together, the wind is going to be sped up. And so when the air is, when you have wide isobars, you have very low pressure gradient. And so as a result, the winds are still moving, in this case, to the east from the west. due to that Coriolis force. And so when we start looking at these geostrophic winds, again, these winds are going to be associated with upper air influenced by the pressure gradient force and the Coriolis effect. We can modify these winds, and we'll get into that in just a second. Now, when we start heating and cooling these airs, what's going to happen is hot air is going to start to rise, and if hot air is going to start to rise, the weight of the overlying air is going to be less. And so as a result, what can happen is if the air in the upper image, this air rising up, the weight of the overlying air is going to be less. And so as a result, it's going to create a low pressure. And if we start looking at air sinking, air cooling down, maybe we have an evening or a really cool surface, say a snow-covered landscape, what's going to happen is it can actually cool the air around it. And if the air is cooling around it, it's going to sink. And if the air is sinking, it's going to have a higher pressure. We can think of the pressure as a scale, the weight of the overlying air. And if I were wearing a backpack here and somebody were pulling up on me, I'd have a lower pressure. If somebody were smashing down on my head, I'd have a higher pressure. And so when we start looking at heating and cooling, these have a direct impact on these pressure systems that start to develop. Now, the first three images are other planets. We've got Saturn, Jupiter, and Neptune here. And if we take a look at these planets here, we don't have the difference between land and water. And as a result, the air is going to rise up around their equators and cause clouds to develop. And so what we have here are some gas giants showing these large clouds to develop. Now, Earth in the bottom image does have gases that actually are rising up around the equator. But we also have to deal with the fact that the Earth is made up of land and water, and this lack of, or this air and water difference is causing some uneven heating of the Earth. Hot air, or excuse me, land heats up a lot faster and land gets a lot colder. And so the result of this is going to cause this uneven heating of the Earth, which is causing these very, very unusual behaviors around these land-water interfaces. If we look at the Pacific Ocean here, we can see that those bands of air, of clouds, are very similar to the bands of clouds on these other planets. So right around the equator, because the sun is shining most directly at the equator, it's going to heat up that area a lot more. Over the course of a year, the most intense rays of the sun are right on the equator, and as a result, it's going to heat up the air. It's going to create that air it's going to cause that air to rise up. Now, when air is rising, it's going to cool off, and as it's cooling off, it can't hold as much water. So right around the equator here, we have this area called the Intertropical Convergence Zone. And as a result of this air rising up, the main movement of air is updrafts. And as this updrafts are occurring, it's going to pull the air from the North Pole, or from the northern hemisphere and the southern hemisphere. Due to the Coriolis effect, these winds are going to be not coming directly down, but deflected to the right in the northern hemisphere, the left in the southern hemisphere. And these are going to be winds moving over the landscape. And so these are definitely going to be winds. So we've got the updrafts right at the equator. The trade winds, primarily from the west to the east, due to the Coriolis effect, it's the northeast trade winds in the northern hemisphere, southeast trade winds in the southern hemisphere. And as a result, these trade winds are going to be exceedingly important. Now, what comes up is going to come back down 30 degrees or so north of the equator and south of the equator. The air is going to sink back down. Winds are still deflected to the right, and so the upper air is going to be deflected to the right. And as that air starts to sink, it's going to warm up. It's going to have more pressure building on it. It's going to be squeezed together a little bit. And so as a result, 30 degrees north and south of the equator are going to be these great deserts of the Earth. and we see things like the Sahara Desert, the Gobi Desert, the Atacama Desert in South America, the southwest part of the United States are kind of in this region. So collectively, this air movement in this circular movement from the equator to the 30 degrees north or 30 degrees south, and then back around, this loop here is called a Hadley cell, a global convective cell where air is rising at the troposphere, moving towards the North Pole or the South Pole, and it sinks back down and moves towards the equator. So this area here is called the Hadley cell. And so we've got the, as a result, it's going to create these winds, again, upper air geostrophic winds moving to the east, but at the surface, these trade winds are going to be very, very important for boat navigational travel, for using sails. So which direction are the winds flowing along the equator? Along the west, to the west, from the east, northeast to the west. And so just to note, when you're starting to look at these questions, if the winds are blowing along, that's where they're going to. If where they're blowing from, it would be the east, in this case, northeast. So I've already mentioned this at the center of the two Hadley cells where the air is meeting. This is going to be occurring at the intertropical convergence zone where the trade winds are meeting. Now, if you were at the equator, again, we wouldn't have, the Coriolis effect would be negligible or non-existent because the air doesn't know whether it should be flowing to the right or to the left. And so right at the equator, there is no Coriolis effect. It's air moving towards the northern hemisphere or towards the North Pole or towards the South Pole, away from the equator, that we start having that Coriolis effect. So as I've already mentioned, right at the intertropical convergence zone, this has tremendous amounts of rain, and the prominent movement of air is up. Now, if you're a sail and you're stuck in this area, you may have heard the term stuck in the doldrums. This term is, this area around the equator is sometimes called the doldrums because it's rainy every single day. The air is moving straight up. And so it's gonna be, this is where we have a lot of our rainforests. If you were in a boat, you could very easily get stuck in the doldrums. You start moving out of the doldrums, oh, those trade winds are going to push you right back in. And so you can get very easily stuck in the doldrums. And that's a terminology that you talked about. People who are in this dark cloud over their heads over day, and so it's very difficult to get out of those situations. So the image on the right here is looking at the air moving right at the equator. Again, you can see those Hadley cells. And so right at this point, pardon me for a second. Sorry about that. So if we take a look at 30 degrees north latitude, this air right here, this geostrophic wind is always going to be moving in from the west to the east. And so this is going to be known as the subtropical jet stream. We also have a polar jet stream. We'll get into that one here in a second. But these two wind belts are moving from the west to the east in each hemisphere. So at any given time, we have 4 jet streams on Earth, 2 in the northern hemisphere, 2 in the southern hemisphere. And this is where these Hadley cells are meeting with a different cell. And so as a result, this air is constantly moving in the same direction. Now we do get bends and kinks in these jet streams, but these winds are moving very fast, 160 kilometers per hour. So that's about 100 miles an hour from the west to the east. In all cases, it's always moving from the west to the east. Again, these jet streams can have bends in them, and these have real big influences on what the weather patterns can occur on the Earth's surface. So they can move low pressure centers or high pressure centers that we'll get into in a second. But each bend is called a Rossby wave, a kink in this jet stream. And just like a stream, it meanders back and forth. So in the northern hemisphere, how many jet streams do we have? We have the subtropical jet stream and the polar jet stream. Again, right here and right here from a three-dimensional image here. So as the air is moving, causing those jet streams to occur, we're looking at the Hadley cell is moving through the atmosphere, but we also have a Walker circulation. This is occurring in over the oceans with this air rising and falling over these large bodies of water. And the reason for this is because we have land, and this land-water interface is going to cause water currents to get moved towards the equator or away from the equator. And so in this case, this trade wind's constantly blowing in this direction and causing this air to rise in the western portion and cool in the southern portion. In South America, it's going to cause the water to move along that Atlantic for poleward water towards the equator. And so you're going to end up with cold water right here, warm water in this direction. And this circulation is called a Walker circulation. And if this Walker, this is under neutral conditions, what's happening with these land-water interfaces. And this is a real big influence because directly associated with these Walker circulations are variances on these Walker circulations. The first one that we're going to be talking about is something called El Nino. Now, during an El Nino event, these Walker circulations slow down. And if these Walker circulations slow down, what's going to happen is air is not going to be brought up as high along the eastern coast of the the Pacific Ocean. And so we don't end up with really strong movements of water. And if we don't end up with strong movements of water along the eastern coast of the Pacific Ocean, we're going to create a thermocline. Now, the reason why it's called El Nino is because it develops around Christmas. And so it was first identified in the 1980s when we started looking at old fishing records in South America. And in those regions, every couple of years, we had a really crappy fishing report or fishing off the coast of South America. And so it was later discovered, we correlated this data in the we looked at this data and we tied this together that we have warmer waters in the Pacific Ocean on this part of the world. At the same time, we have lack of upwelling, the reason why we have crappy fishing is because we haven't broken that thermocline. We talked about this in the chapter on oceanography, where this water, most years, the water would be brought up. We'd bring cold, nutrient-rich waters with breaking the thermocline. Algal blooms would occur right in this region. And if we had algal blooms accumulating, we'd have organisms eating those algae. And so this would be a great place for fishing, but we don't have it on El Nino's years. And so the correlation was made that this impact of El Nino, or this lack of upwelling, had really, really, really bad weather, had influences on weather throughout the rest of the year. So during an El Nino year, the rest of the planet actually is affected. So as a result, the Pacific Northwest ends up with cool, wet environments. In the Gulf area, we end up with warm conditions. In the upper east part of the Midwest, in places like Ohio, we end up with really wet conditions in their winter. In areas like Africa, we end up with cool portions of the Atlantic Ocean, excuse me, of the Atlantic Ocean, cold and wet conditions down in southeast part of Africa. And so the impact of who knew the impact of the largest ocean on the planet has an impact on, affects the rest of the weather patterns throughout the rest of the Earth. So we can definitely see the interconnectedness here. Now, there are other times that we end up with a really active Walker circulation. And this really active Walker circulation is going to cause massive upwelling. And so the water in the Atlantic or in the Pacific Ocean right here is going to be moving a lot of that cold water. And so these are going to be hyperactive movements of these trade winds pulling up this water along the Pacific Ocean. And it too is going to have its own set of weather patterns. And so during a La Nina year, now in the winter of 2020, we're experiencing a La Nina year. So we're going to experience a little bit wetter portion to the south of us and a little bit warmer to the north of us. Here in Missouri, we're not as affected by El Nino as other parts of the world are, but there's definitely an effect. So what happens during an El Nino year? Walker circulation weakens during an El Nino, spreading warmer water to the eastern part of the Pacific Ocean. This in turn has a real big influence on the rest of the circulation. So the answer would be D. Now, we really haven't talked too much about this yet, but we will, that there's a huge variance in seasons. And so as a result, the reason why we have a variance in season is that the Earth is going around the sun. And so we can see this image here, and this is showing the axis of the Earth at two different seasons. In the left part, we can see that the Earth is, the North Pole is tilted toward the sun. So here in Missouri, we have long days, short nights, the sun is high in the sky, and so this is our summer. Our winter, on the other hand, is the Earth's axis is tilted away from the sun, and so we have long nights, short days, and so this makes a lot of sense to us here in Missouri. But I want to kind of focus on where the direct rays of the sun, this technically is called the subsolar point here, that the sun is shining directly at the Tropic of Cancer here and the Tropic of Capricorn here, 23.5 degrees north and 23.5 degrees south. And incidentally, this is one of the ways that we humans have found the size of the Earth, because if you were on the tropic at the start of spring or the start of winter, excuse me, the start of summer or the start of winter, you would not have a shadow. The sun would be directly down. If you were further away, you'd have a bigger shadow. If you figured out the size of the shadow compared to the size of the distance you were away from the Tropic of Cancer or the Tropic of Capricorn, you could then calculate proportionality and figure out the size of the Earth. Now, the point in talking about this intense rays of sunlight, because this is going to influence where our Hadley cell is starting and where our Hadley cell is sinking. In particular, where the Hadley cell is hitting most, where the sun is hitting the most directly, that's going to cause the most uplift of air. And so we call that the intertropical convergence zone, where those two Hadley cells meet. And you can see here from this image that in July, the Hadley cell is significantly further north than it is in the south in January. And so if we didn't have land and we had even heating of everywhere on Earth, we'd have perfectly straight lines. But because land and water heat up differently, we have a variance in that, and it's not a straight horizontal line. You can see that the biggest bends are where we have that land-water interface. Now, I do want to kind of focus on a place like a place like the Indian Plains of the subcontinent of India. So if we take a look, this intertropical convergence zone in India here in July, air is moving we have the trade winds moving towards the intertropical convergence zone here, off of the water, up onto land. And when air is getting forced up, what's going to happen is it's going to get forced up. When air is rising, it can't hold it's going to cool off, it can't hold as much water, and it's going to rain. Now, the Arabic word for rainy season is called monsoon. And so the book talks about monsoon as this changing air circulation accompanied by a rainy and then further by a dry season. So when we have this monsoon season in the summertime, the air is off of the ocean onto land to create this monsoon. 6 months later, if we go back to this image, the intertropical convergence zone. So now we're in the North Hadley here, and the air would be moving from the equator, from India down towards this intertropical convergence zone, south of the equator. And as a result, the air would be moving from the north, from the Himalayan mountains, off of the Himalayan mountains into the Indian Ocean. And so the air moving down is going to have no moisture in there, and so it's going to be this drying air. So which of the following is defined by a seasonal changing in air circulation? It's that monsoon season. And so when we start looking at monsoon season here in India, the impact is quite stark. If we start looking at India in December versus India in July, we have rainy season and dry season. Now, if we go back to this image, we can see that we actually have air moving either to the north and to the south in this portion. And so these Hadley cells do, in fact, the air moves in when the sun is highest in the furthest north. What's going to happen is it's going to create those Hadley cells. And so in the US, we do have a monsoon season in the southwest part of the United States in early July, where we have sudden downpours, isolated flooding, and widespread lightning. It's not nearly as intense as what we have in India, but it still is crucial, something to be looking out for, especially if you're, say, in the southwest part of the United States on summer vacation. So when we start looking at the mid-latitudes, so this is looking at the northern edge of those Hadley cells, and then we have a mid Hadley, a mid cell as well, a mid-latitude cell. And this is from 30 to 60 degrees north latitude. And this air is the result of the polar air moving down and the warmer air from the equator moving back up. So if we slide back to that Hadley cell, way back at the start of this chapter, when we started looking at these Hadley cells, we can see that where the air is sinking back down, what's going to happen is that air is going to be moving from the west to the east. And then in this area, we have at the North Pole, we have the polar vortex where this cold air is most compact. It's going to be moving away from the North Pole, and it's deflected in the northern hemisphere to the right. And so what's going to happen is that air is going to be moving from the northern hemisphere in this general direction from the east, and the air over here is going to be, as it's sinking from the edge of this Hadley cell, it's going to be moving from the west to the east. And this is dominated by the Coriolis force, and so this is going to be causing the um, westerly winds. And these are, again, driven by other winds, and so they're not as consistent. And so we started looking at those trade winds, and where these two air masses were meeting are called the polar front, where the westerlies and the easterlies, the air near the northern hemisphere are meeting, are called the polar front. And so where those air masses interact, they can cause lots of circulation. And so we start looking at the polar jet stream, and this polar jet stream can have some waves associated with it. Again, the same reason that we have seasons. Those intense rays of sun are going to be in the winter are going to be moving further south. In the summer, they're moving further north. And so when we start looking at the polar front here, it's a result of those seasonal differences. But in all cases, the winds are moving from the west to the east. In the spring, we have a lot more variance, and I'll talk more about that in our chapter on severe storms. So which direction the polar jet stream flows? From the west to the east. Now, I've mentioned this a couple of different times, but I haven't really explained why. When we start looking at land and water, land becomes much more extreme. It's going to heat up a lot more. It's going to cool off a lot more. It's a really poor insulator. Water is a really good insulator. It takes a lot of energy to heat up water, and that energy can be held in the water. It takes to heat up and cool off water is it's one of the hardest substances to heat up. And so we can look at this as its heat capacity. It can store a lot of heat. The oceans are great at storing a tremendous amount of heat. When water evaporates, it's giving off that latent heat, and so this is one of the reasons why hurricanes can be so devastating, is because of the high amount of energy that's in this warm water. Now, if we have a coastline, we're going to have land and water, and it's going to get the same amount of sunlight. But what's going to affect the sunlight is the difference between the land and the water. So one of the things that's going to happen is if the sun is hitting this land, the land is going to have a higher it's going to be absorbing more sunlight. It has a lower albedo. Albedo is the measurement of how much sunlight can be reflected. And water has a pretty high albedo. It's going to reflect a lot of sunlight. The other thing is that water is transparent. And so some of that sunlight can go into the depth of that water. That sunlight at the Earth's surface is going to be trapped at that Earth's surface. The other thing that can happen is that water can evaporate, and evaporate is going to take with it some of that extra amount of heat. So all of these reasons are going to cause the air right above the water to be significantly cooler and at a higher pressure. The air over here is going to heat up a lot. Hot air rises, and so as a result, it's going to cause this air to rise up. Now, we always call breezes from which they are coming from. And so if I have my freakishly large head here on my person here, what I'm going to have is air moving from high pressures to low, just like we started this chapter with. And this is called a sea breeze. And this is going to be happening as the day, because this area is going to heat up. Now, at night, the exact opposite is going to happen, where the water, again, because it retains its energy, it retains that heat, the land's going to cool off. And so these are going to switch. This is going to be the high pressure. If I was still on that same spot, the air is going to be moving from the highs to the low, and we'd have a land breeze. And so that's an example of a local breeze. Some other local effects are these lake effect storms. And if we look at the Great Lakes, we can see that these Great Lakes are occurring here. Winds in the mid-latitudes are from the west to the east. And in the in late fall, early winter, what's going to happen is the water is going to be a little bit warmer than the air. And so what's going to happen is you're going to get a lot of evaporation taking place on the Great Lakes. And so as a result, if you are to the east of these Great Lakes, what's going to happen is this high amount of water is going to be in the air. The air is going to be blowing from the west to the east. And so you're going to be putting up a bunch of water into the air. The air now is over this ground, which is going to be very, very, very cold compared to the water around it. And so it can start to condense. And so as a result, it's going to create this thing called lake effect snow. These can be really, really pronounced, particularly if we have a cold front come through early on in late fall, early winter. This can where the waters are still really warm and evaporating out a lot of water, which are going to fall as this lake effect snow. So what time of year? That would be early winter. Late fall, early winter. Another local breeze can occur in differences between land and valleys and mountains. Now, during the day, what's going to happen is the valleys are going to be a little bit cooler than the air around it. And so the sun is going to strike these mountaintops. And so it's going to heat up this air. And it's going to create this circulation, cause this air to rise up as these red arrows are occurring. And so if you were standing right here, the air would be from the valley moving upward. And so we'd call this a valley breeze. At night, what's going to happen is the mountaintops are going to cool off faster than the air in these valleys. And so as the air in these valleys are going to, the cold air is going to sink into this area. Cold air is more dense than warm air. And so in the night, you end up with these mountain breezes. Now, I know that as I'm recording this is in prime hunting season. And we know that deer are really good at smelling human scent. And so knowing which direction the wind is blowing, it's going to be having a tendency, even on these little microclimates of these little hills of Missouri, we have these valley breezes and mountain breezes. So you may want to position your deer stand differently in the night versus in the daytime, in the evening and in the early morning, because of these differences between these different breezes. Some other local effects is we have a prominent wine industry. And so the valleys are going to be closer to freezing in the winter time. And so if you wanted to pick your grapes at the peak time before they froze, where the sugar content would be the highest, I would start in the valleys because that's when you're going to freeze. If you froze the grapes, you'd end up with the grapes freezing on the vine and all kinds of problems associated with that before you could press them into wine. So we have lots of examples of these winds. Another common wind is we have air getting pushed up over the side of a mountain. And when the air is pushing down to this lower pressure zone, these can create some very strong winds. In particular, when we start looking at the winds, in this case, the air is getting pushed up over the mountains. It's going to drop out all its water on this side, on this windward side of the mountain. And so if all of the rain is going to be occurring over here, this air down here is going to end up moving very, very violently down the side of the hill, and it's going to have no moisture in there. So you have very, very low humidity. And if you heat up this air, it's even going to be drier, and it can actually dry out the air on this side. And unfortunately, Some good examples of this would be the Santa Ana winds, which are famous for wildfires, which currently, as I'm recording this, are pretty dominant in these western states, where we end up with these winds. And again, we've been talking about winds, not just in this earth science class, but when I asked the question at the beginning of the semester, how does earth science influence you? I think most people actually talked about the weather, and it definitely does. And you're not alone in this. When we start looking at these winds, people have been talking about these winds for a number of different millennia and given them separate different names. And so different cultures have given different winds different names. And so the Santa Ana winds or downslope winds occur because of the pressure difference on opposite sides of the mountain here. Again, higher pressure on this, in this case, on the left side of this image, and then the shortening airflow on the eastern side are creating these very strong, hot, dry winds coming down the side of the mountain. If we have a dome of cold air coming down off the side of a mountain, off, say, an ice sheet or a glacier, we can have these cold, dry airs moving down, creating these very strong winds called catabiotic winds off the coast of Antarctica. And so here's an image of some of these local names of these local winds. Again, this is based on the geography and these land-water differences heating up. These can be caused from air being pushed up over mountains. And so lots of different cultures have identified these things. And so we are not the only part of the world that is directly affected by earth science here. So if you have any questions about this chapter, please let me know.